The battlecruiser HMS Queen Mary was destroyed in moments when enemy shellfire is believed to have triggered a catastrophic magazine explosion. On May 31, 1916, the colossal warship engaged German battlecruisers during the Battle of Jutland. Most accounts attribute the fatal hits to SMS Derfflinger, whose armor-piercing shells struck the forward part of the British vessel. The exact path of those shells through the armor and internal spaces cannot be reconstructed with certainty from the surviving wreckage. What can be stated with confidence is that the hits set off an irreversible and fatal chain reaction deep within the hull. The primary impact appears to have ignited cordite propellant charges somewhere in the forward ammunition system. Cordite did not behave like conventional high-explosive bursting filler. It burned with savage speed, producing a flash fire capable of moving through exposed handling routes and ammunition passages if anti-flash precautions failed or were bypassed. On HMS Queen Mary, the accepted explanation is that cordite flash reached the forward magazines and turned a localized hit into a ship-killing magazine explosion. The resulting magazine explosion generated a massive expansion of superheated gases inside reinforced compartments never meant to contain such violence. The confinement of the magazines and surrounding structure gave the blast nowhere to expand harmlessly. When that containment failed, the forward sections of the battlecruiser were torn apart from within. Heavy framing, plating, turret structures, and ammunition spaces were violently disrupted and scattered across the seabed. The forward part of the heavy warship was effectively destroyed in an instant. With its forward structure and buoyancy gone, the remaining battlecruiser lost stability and vanished beneath the North Sea within minutes, leaving no realistic chance for organized evacuation. 1,266 crew members were lost, while only a tiny number survived the sinking. When the shattered remains of the warship finally settled on the ocean floor, they formed a highly complex and chaotic debris field. The ruined hull contained the precise physical evidence needed to understand exactly how the internal protections failed. The twisted internal bulkheads and torn external armor plates held the exact forensic signature of the overpressure event. Naval architects and marine forensic engineers desperately needed to read that ruined steel to fully comprehend the mechanics of the destruction. However, the massive and instantaneous loss of life imposed a powerful ethical boundary around the wreckage. The sunken battlecruiser was no longer just a scattered piece of military hardware awaiting forensic recovery. It was a naval grave holding 1,266 lost men. Long before formal legal protection arrived, any intrusive recovery would have meant disturbing the resting place of the crew. No respectful investigation could treat the separated structural sections as ordinary scrap. No engineering team could justify cutting into the remains simply to satisfy a forensic question. That conflict defined every later investigation. The steel had to be read as evidence, but approached as a grave. The wreck remained a shattered puzzle on the seafloor, legally and ethically beyond intrusive examination. The heavy steel wreckage rests in a high-risk operational envelope beyond conventional observation and below the easy reach of surface inspection. The North Sea adds severe surface weather and brief operational windows, sometimes forcing survey ships to abandon their coordinates to avoid structural damage. Below the turbulent surface, the site is subjected to persistent tidal currents that sweep across the relatively shallow continental shelf. These water movements can stir loose sediment, sand, and biological debris from the seabed. This mechanical agitation creates a difficult visual environment for survey teams. At roughly 60 meters, or about 197 feet, the site sits in low light, heavy turbidity, and frequent optical denial rather than a world of absolute perpetual darkness. When survey teams lower artificial light sources into this specific environment, they can hit a thick wall of suspended particulate matter. The powerful lights reflect directly back into the optical sensors. The resulting visual backscatter can reduce practical visibility to a narrow working envelope. A standard submersible camera system cannot easily establish the standoff distance needed to image a massive battlecruiser structure without losing detail in the murk. To properly understand the geometry of a giant warship, surveyors need more than isolated close-up views. Those conditions made wide-area geophysical mapping the first credible route to comprehensive interpretation. Beyond these formidable physical oceanographic limits, a secondary administrative boundary eventually reinforced the wreck's protected status. As offshore technology advanced, the threat of unapproved commercial interference grew. The British government moved to formalize protection for the battlecruiser and other naval graves. In 2006, the United Kingdom designated HMS Queen Mary by vessel name under the Protection of Military Remains Act. That designation meant any place containing her remains became a protected place. It did not create a published coordinate grid for Queen Mary or convert the wreck into a controlled site boundary. The designation protects the place containing Queen Mary's remains without turning the wreck into a published exclusion grid. The practical rule is simple: look but do not touch. Non-intrusive observation may be possible under appropriate conditions, but interference, removal, penetration, cutting, or recovery without a license is an offense. Salvage crews and commercial operators therefore have no authority to remove artifacts, break into compartments, deploy grabs, cut plates, or lift material from the protected remains. The state retains ownership of the warship, while the legal protection focuses on preventing unauthorized tampering with the vessel and its contents. The convergence of difficult visibility and strict non-disturbance rules created a significant engineering paradox for marine investigators. Naval historians and structural surveyors required precise, large-scale geometric data to understand the exact layout of the heavy wreckage on the seabed. However, they faced a war grave they could not lawfully disturb and a massive target they could not easily see. Investigators could not excavate buried plate edges, lift torn sections, cut through armor, or clear sediment simply to improve the forensic record. Any useful close observation, therefore, had to remain passive, and any method that depended on physical disturbance was off limits. Overcoming the depth and visibility constraints required a method to map the chaotic site without violating the prohibition on intrusive work. Advanced acoustic technology completely bypasses the severe optical limits of the deep ocean by mapping solid structures with focused sound waves instead of ambient light. A specialized survey vessel deploys a multi-beam echo sounder array directly beneath its hull. As the surface ship moves slowly along a highly controlled grid pattern over the target zone, the array emits thousands of precise acoustic pulses downward through the water column. These sound waves travel perfectly through the dense, suspended particulate matter that completely defeats standard optical cameras. When the acoustic energy strikes the dense steel sections resting on the seabed, it reflects directly back to the sensitive receiving transducers on the surface vessel. By measuring the exact microsecond return time of every single acoustic ping, the onboard computers calculate the precise distance to each point of impact. The system is incredibly sensitive. It detects the difference between the hard return of flat armor plating and the soft return of accumulated seabed mud. Millions of individual data points are rapidly collected as the surface ship maps the acoustic grid. Specialized software algorithms then stitch these distinct acoustic returns together to generate a massive three-dimensional point cloud. This digital map turns the debris field into readable geometry rather than isolated glimpses. It renders the exact geometry, orientation, and layout of the entire debris field without requiring a single piece of physical equipment to touch the wreckage. While acoustic mapping establishes the exact macro structure of the scattered hull components, marine surveyors still require high-definition optical verification for fine detail analysis. To achieve this without violating the strict no-touch policy, engineers deploy remotely operated vehicles. These heavy industrial submersibles are connected to the surface ship via long armored umbilical cables. Highly trained pilots fly the massive machines down into the darkness using powerful electric thrusters to maintain precise and highly controlled standoff distances. The vehicles are equipped with high-intensity lighting and advanced focal-length cameras designed specifically for underwater distortion correction. Because the acoustic point cloud has already mapped the exact location of every steel hazard on the seabed, the submersible pilots can navigate safely through the treacherous, jagged debris. They do not have to search blindly. They fly direct routes to specific targets identified on the sonar map. The pilots slowly maneuver the sensitive cameras to within inches of the torn structural margins without ever allowing the heavy frame of the vehicle to make physical contact with the protected site. This disciplined operational restraint allows the engineering team to capture critical, high-resolution visual data while strictly adhering to the mandated survey boundaries. The electric thrusters are constantly adjusted to fight the local currents, ensuring the submersible remains completely stable and never accidentally drifts into the historic steel. A single non-intrusive survey provides massive amounts of data, but it only captures one moment in time. Early visits and surveys from 2000 to 2003 created crucial reference points for the massive site. Later, ROV and multibeam work gave researchers a way to compare the wreck's changing condition against those earlier observations. By recording position, orientation, and the visible condition of major steel masses, surveyors created a practical baseline rather than a perfectly scheduled decadal monitoring program. If a hull section collapsed or disappeared between surveys, the next sonar or ROV pass could reveal the change. Together, wide-area acoustic data and careful optical verification transformed isolated visits into a usable non-contact baseline. Generating a high-resolution acoustic model finally allowed engineers to read the wartime damage, starting with the primary blast zone. The exact trajectory of the incoming enemy shell that destroyed the warship remains permanently unknown because the specific armor plates it pierced simply no longer exist. When marine surveyors analyzed the high-resolution acoustic data of the main forward hull, they encountered an extreme forensic limit. The raw explosive force that shattered the bow completely annihilated the physical record of the initial strike. The steel was so thoroughly torn and scattered that tracing the initial entry hole through the heavy outer citadel is a physical impossibility. Despite this profound blind spot, the non-contact survey still captured critical positive knowledge. The mapping operation defined the broad geometry of the forward debris field and helped identify the likely zone of catastrophic failure. The forward section of the battlecruiser is not a cohesive hull piece. It is a fragmented collection of heavy steel components spread across the seabed. This distribution is consistent with a catastrophic magazine explosion and breakup rather than slow seabed decay. Heavy armored barbettes, main guns, and turret structures were displaced from their original positions. By measuring the final resting positions of these heavy components, surveyors could map the scale and direction of the wreck scatter. The pattern strongly supports an explosion centered in the forward ammunition spaces. The forensic analysis of this blast geometry allows marine engineers to infer the scale and direction of the destructive event without needing to enter any internal compartments. The twisted orientation of surviving girders and the displacement of heavy armored elements point back toward the forward ammunition spaces. The acoustic point cloud does not calculate the exact volume of propellant consumed, and it does not solve the explosion as a perfect equation. But it does preserve the final arrangement of the heaviest surviving elements on the seabed, giving investigators a powerful non-intrusive record of how violently the ship broke apart. That same macroscopic violence also set the proof ceiling. The forward upper deck and side armor panels were mixed into the chaotic scatter, with thousands of jagged fragments produced by the internal outward shockwave. Furthermore, the strict ethical boundaries lock this forensic ceiling perfectly into place. To firmly prove the exact entry path, investigators would need to physically dredge the forward impact crater and extract thousands of heavy steel fragments to the surface. They would have to physically reassemble the torn armor like a massive shattered jigsaw puzzle to find the primary puncture. Because the designated site mandates a strict zero disturbance policy, surveyors cannot lift a single piece of steel from the mud. They cannot clear away the heavy accumulated sediment to look for entry holes on buried structural fragments. Engineers must accept the physical reality of the extreme fragmentation. The main forward hull yields absolute proof of the internal epicenter and the massive radial blast geometry. It scientifically confirms the complete structural failure of the forward citadel and the violent ejection of the heaviest gun emplacements. That limit is equally clear. While the forward hull confirmed the violent mid-water disintegration, the largest intact piece of evidence lay hundreds of feet away, holding a completely different set of answers. When marine surveyors analyzed the detached stern section, they found a massive physical contrast to the shattered forward wreckage. The rear portion of the warship had separated from the primary blast zone and sank independently. It came to rest away from the forward wreckage, inverted and still largely cohesive. Early observations showed that around half of the ship lay upside down and, although collapsing, remained largely intact. But it was not a perfectly sealed steel vault. A split in the upturned hull offered a view into the magazine beneath X turret, proving that parts of the interior could be seen without cutting new access into the wreck. The lower engineering spaces still remain difficult to verify internally for the same reason. However, when researchers resurveyed the site with ROV in 2014, the earlier condition of the stern section had dramatically changed. High-definition optical sensors revealed that areas previously seen through the split in the upturned hull had been flattened and open. The magazine area beneath X turret, once visible inside the wreck, now showed shells scattered through collapsed structure. This rapid change did not match a slow, even pattern of natural decay. It pointed instead to recent disturbance of the largely intact stern. This catastrophic collapse did not match the slow biological decay of a submerged wreck or the sudden outward violence of a wartime deflagration. The comparative structural baseline proved this was a highly calculated and methodical artificial extraction. The torn external plating aligned perfectly over the specific location of the internal engine rooms. Unidentified commercial operators deploying massive industrial salvage grabs had physically smashed through the legally protected historical boundary. They dropped incredibly heavy mechanical claws from commercial surface vessels directly into the inverted stern section. These industrial scavengers were apparently seeking high-value non-ferrous metal housed inside the machinery spaces. Evidence reported from the looting included cordite containers, at least one condenser, and a gun tampion identifying the wreck. The ship's condensers sat forward of X magazine, and removing one from the largely intact hull would have required serious disturbance to that area. The recovered condenser was reported to be worth at least 65,000 pounds. For pure commercial profit, the salvers damaged a protected naval grave and destroyed part of the surviving structural record. By comparing the largely intact condition recorded in 2003 against the damage seen in 2014, surveyors separated wartime destruction from later disturbance and documented collapsed structure, exposed shells, and damage in the area associated with condenser removal. The remote mapping technology captured the changing seafloor geometry without invasive equipment, turning the detached stern into evidence of deliberate industrial destruction. That evidence forced a confrontation between scientific baseline mapping and the complex reality of oceanic law enforcement. The law expressed a clear sovereign intent. The United Kingdom retained ownership and prohibited unauthorized disturbance. The weakness lay offshore, where known wreck positions, GPS, sonar, and distance made a remote naval grave targetable beyond ordinary coastal policing. This geographical reality creates a serious enforcement problem. Domestic legislation carries immense moral weight and can create offenses, but its practical reach outside territorial waters depends on nationality, flag state, evidence, and international cooperation. A sovereign decree printed on paper cannot physically stop heavy commercial vessels from approaching a remote wreck. Sustained patrols over a remote North Sea wreck are economically and operationally difficult, and the same hostile environment that once shielded the steel now works against enforcement. In practice, investigators must link vessel activity, recovered material, seabed damage, and eventual scrap movement into one evidentiary chain before origin can be proved. Because continuous physical guarding remains impossible, maritime authorities and researchers are forced to rely on intermittent reports, vessel monitoring where available, and return surveys of the seabed. Unauthorized salvers can exploit distance, busy sea lanes, poor weather, and the difficulty of proving exactly what happened below the surface. Their advantage is temporary access, remove the metal, merge back into commercial traffic, and leave investigators trying to prove origin after the evidence has dispersed. This severe operational gap leaves the surviving sections of the battlecruiser completely exposed. The heavy forward wreckage and the remaining intact engineering spaces are now permanently subjected to predatory industrial targeting. The practical response is reactive, flag anomalous ship movements when satellite or vessel data allows, then schedule another acoustic survey months or years later. The original baseline acoustic map intended to monitor slow natural corrosion now functions strictly as a high-definition crime scene ledger. When the non-contact survey teams return to the site, they continue to strictly obey the zero disturbance mandate. The pilots carefully fly their sensitive cameras around the massive new tiers in the outer armor. They meticulously record the freshly exposed structural internal ribs and log the missing engineering valves. The survey record remains precise, but precision does not prevent the loss. The mission solved the mapping problem, not the protection problem. Queen Mary could be documented without contact yet still dismantled by operators willing to violate the boundary.